The title of my talk has changed a little bit because my plan to, show you something about a study about the evolution of ambiguity. It's a very specific kind of model, and I would like to introduce you to, or give you a big picture of what you can do with the game theory when you want to study language evolution, especially to a specific kind of game type. It's called a signaling game. Then I want to introduce very basic mechanisms of evolution. So I will introduce basic mechanisms of evolutionary game theory and some ideas about how learning dynamics might work with this kind of games. So this would be a little bit going in the direction of multi-agent research. I will show you some applications, so stuff that has been done with this kind of models in language evolution research. And then if I have time left, I will present you my case study, but I will probably go very fast through it. And if you're interested in it, I can send you more material about it, because this case study, again, is very specific. Okay. So first of all, I would like to ask you if you see this kind of silhouette of an animal. So you might be wondering, what is this animal? So has anybody an idea what this is? Yeah? A wolf? Something else? Other guess? A dog? Perfect. That's what I wanted to hear. This was not planned with the people, so we have a game. And so you might be not sure if this was a dog or a wolf. So I want to tell you what it is. Since I cannot, let's say I know it. I know it's a dog or a wolf, so I cannot put my thoughts and my information into your head. I have to communicate it somehow. So what we have two sets. One set is what I have in my head, and the other set is what you could decide what this might be in your head. So T is for, let's say, information states. The T comes originally from types and A from actions, because these models come from animal signaling kind of literature. But let's call it for human communication, information stage and interpretation states. Now, this example is about that we want to communicate successfully. So I want to put my thought into your head. And this is then given by this game, what's the coordination game. So this kind of standard signaling game is based on a coordination game. So the standard assumption is that we have a common interest of successful communication. And of course, there's a lot of literature that is altering even this kind of conditions to that our interests are not completely aligned. I want to send a fake signal to believe something that is not true, and so on. But let's focus in this little example on this kind of game. Now what we can have is we can have so-called prior probabilities. These are, for example, probabilities how probable it is to see a dog or a wolf. And then, of course, I want to communicate, so we have a set of messages, M, and let's say these are completely random messages here, da and do. And this game, this simple game, is called a Lewis game, because this idea is based on David Lewis' book from 1969, Convention. It was, in fact, his dissertation. And this would be the extensive form of this kind of game. So what happens is you have a player called nature who is just drawing, in this case, with the prior probabilities, the situation. The situation is we see a dog or a wolf. And then S is a sender who can choose one of two messages. And then the receiver or hearer receives this message and can choose D for dog, W for wolf. And then the score is according to this utility table. This is called extensive form game. And this line here represents information states that the receiver cannot distinguish among. Okay, so what you can do now is you can describe this kind of behavior as strategies. For example, as pure strategies are kind of functions. So if we want to explore the whole strategy space, we could have this kind of all possible different combinations a sender could use. So I could use da for dog, do for wolf, like in S1, or in S4 I could use do for dog and wolf. And of course we can do the same for the receiver. So what I have done here is I have transferred this extensive form of possible situations in a set of strategies. And this is very helpful if you want to use evolutionary game theory, because now you have a set of fixed strategies and you can compute expected utilities over the strategies. So remember we had this, this utility table here, and if we compute expected utilities, I don't have the formulas here, but just believe me, we can measure how well the strategies work together, and you got this kind of expected utility values. And if you go back, or if you look at the combinations that are very successful, we see S1 together with R1 and S2 together with R2 are the most successful ones in terms of expected utility, and these are exactly the combinations who would really differentiate between different states and the sender-receiver strategies that fit perfectly together. And you can, if you analyze this kind of table, you find out that these are strict Nash equilibria, and Nash equilibrium is a strategy that is, or a strict Nash equilibrium whose value, first value is the value of the sender, is maximal in a row. The second value is the value of the receiver. It's maximal in over all columns. And if you get this maximal values, you have a strict Nash equilibrium. Okay, so this is very important because the strict Nash equilibria tell us what people, they don't tell us how people come into this kind of situations or develop this kind of strategies, but they tell us once they are in this kind of strategies, they wouldn't change it. Because they, under the assumption that we are rational agents who try to maximize utility. Utilities are preferences, so we want to maximize our preferences, so we stay in this kind of states. Now, what we can do now with the strategies is we can say, okay, a person is not only a speaker or not only a hearer or receiver. We do both. Sometimes we speak, sometimes we listen to others. So we can combine this, and we got strategy pairs. And I just picked out, there's in this game 16 possible strategy pairs. I picked out 3 strategy pairs just for exemplification. And you can again do this kind of utility matrix. You can have a formula how to compute expected utilities. The assumption is that people are 50% speaker, 50% hearer. You get this kind of matrix, only for these 3 strategies. And you can analyze this again. This is a symmetric matrix now. Remember before we had here senders and here receivers. Now we have strategy pairs. So the strategy sets are the same for column and row players. So we have a symmetric matrix. And with this kind of game, we could analyze what happens for different population states. And a population state is just defined by a vector who tells us how much of a population plays specific strategy. So what we're doing is we're looking at this kind of strategies as frequencies that are used in a population. And this strategy would tell us if the first position stands for sigma 1, strategy sigma 1, would tell us the whole population is playing this strategy. So you can have also this kind of mixed population states that half of the population is playing sigma 2 and sigma 3, and so on. And a very popular dynamics in evolutionary game theory is the rapid color dynamics, who tells us how population shares, how this kind of vectors would change over time, for example. And you can, of course, analyze all possible dynamics. It's not important what kind of. I mean, it's important because you want to have a dynamics that also somehow matches the properties of the phenomenon you want to model, right? But I just picked out one, and you can use all possible ones. This is a quite simple one, and these dynamics tell us that how a population share of a specific strategy changes over time, and it just says that if the strategy is better than average over all strategies, its frequency increases in the population. If it's worse, it decreases. Okay, that's what I just said. So you can, for example, when you have 3 strategies, depict the situation on a simplex. So a simplex just tell us each point in this kind of simplex is a population state. For example, this point tells us that everybody is playing sigma 2. This point tells us that half of the population is playing sigma 1 or sigma 2. And then if you get the point in the middle, it's 1/3 of each strategy. And these arrows are kind of sample trajectories for different kind of states under the replicator dynamics. And what you, for example, see for the specific game I showed you is that all these kind of arrows go either to sigma 1 or to sigma 2 for the given game. And this area, for example, from which all arrows go to the specific strategy is called its basin of attraction. So this strategy has a basin of attraction of half of all population states. And we have also equilibria in the middle, and these are unstable equilibria. So if they would, the population would stay in this state as long as there's no noise mutation or something like this. A little bit of mutation would put the system away and into one or the other kind of systems. And this is interesting because you can study not only the dynamics but also the stability. Again, if you look at this table, we already know that these are strict Nash equilibria, and it can be shown that strict Nash equilibria are so-called evolutionary stable strategies. In fact, there's a specific relation between Nash equilibria, evolutionary stable strategies, and non-strict Nash equilibria. The concept of an evolutionary stable strategy comes from theoretic biology, and it has specific nice properties. For example, an evolutionary stable strategy has an invasion barrier. What does it mean? If we go back to this picture, so this strategy has an invasion barrier because when we are in a situation where everybody's playing sigma 2, the whole population, and mutation or invasion moves the system a little bit in this direction, then the evolutionary dynamics would always leave it back to this. So you need really strong shocks to leave really this area and come to the other strategy. Of course, evolutionary stable strategy only tells us the strategy has an invasion barrier, but it doesn't tell us how big this invasion barrier is. Technically, if you would have a small invasion barrier like here, it would still be evolutionary stable strategy. So there's also a degree of stability among this kind of strategies. Okay. So this is what I just said. Okay, and so what we just found out, what I just showed you is, and you can analyze the whole strategy space, 16 times 16 strategies, and what you will find out that there are only 2 evolutionary strategies, and these are exactly these strategies here that distinguish, that use both words da and do to distinguish between a dog and a wolf. Okay, just to make sure, this is just a dummy example. It was studied a lot in philosophy, for example, and later I will show you that also much richer kind of linguistic features can be studied with this kind of models. But it gets very complex and the strategy space gets very big. So that's why I show you this dummy example. Okay, and we can do this. So we can make a mathematical analysis and find out the stability aspects of different strategies, or we can do a learning model. So then we go in the multi-agent direction, where we, because what I showed you before is we abstract from an agent-based view, and we take a look of a population-based view. Now we go back to the agent-based view here because maybe we want to implement more specific features, or we want to implement stochastic processes that we cannot analyze that easily, at least with evolutionary game theory. So we can do what Luc Steels talked about. We can do simulation experiments with, for example, learning or imitation dynamics. So I'll show you just very fast learning dynamics that is called reinforcement learning. So what we have here is we have the speaker who has this on his mind. He wants to communicate either dog or wolf. We have the receiver who wants to construe the right thing, and we have 2 messages that can be used. And the simple model of reinforcement learning can be defined with kind of urns. So we have specific urns for dog and wolf with different balls for the different messages here. And then what happens is we pick, nature picks dog in this situation. So I want to communicate dog. So I just draw randomly a ball from this urn. So I have a stochastic process here. And then let's say I drew a red ball. I use da. Now what the receiver has, he has different urns for different messages with balls for different interpretation states. So he has to draw from the red urn because he gets a message da. Let's say he draws a white ball. What means communication is successful. Of course, there must be some kind of feedback mechanism. The standard model abstracts from this. We saw in Luc Steels' talk that it's also good to have feedback that it worked or not. In this case, you can also see if communication works the species survives, or this is a situation I survive because I do the right turn if a specific predator attacks me. So this might be the utility here. Of course, you need more elaborated types of feedback. It's not in this model, but so both know if this was successful or not, and the urns go updated. So what happens here is we have one red ball in the white urn, and the same happens there. So replace urns here. In the standard model, you don't replace, you put a new ball in, but let's, for simplification, say we replace. And what happens after a while is that in this kind of simple game, after a while, we have this happens in all simulation runs at the end. We have one urn with only red and the other with only blue balls, and this happens for the receiver again. And what they have learned is a signaling strategy. So the same that we figured out are evolutionary stable under evolutionary dynamics. Exactly these two. And this is what Lewis called signaling systems. Okay. So why should I use game theory for this? You could say, okay, you can use a kind of other kind of communication models. You don't need the signaling game to do this. What's nice about this is you have many ready-to-use tools from evolutionary game theory and learning models, and you can, for example, if you keep your model very simple, do mathematical proofs of stability aspects of it, for example. And this is very helpful to see if your prediction work for the basic model, and then if you want to have a more complex model, you can go to learning models. And often learning models and evolutionary dynamics kind of behave in the same way. Not always, but very often for a lot of games. And this is what you can also test. So you have different perspectives, as I just said, when you use a different kind of tools, population-based or agent-based. The analysis is either formal or computational, then with simulations. It's also that you normally have a static model and more stochastics for learning models. Don't take this as a hard cut here, because you have also tools in evolutionary game theory to deal with stochastic models. But if you have a lot of noise and a lot of factors that it's hard to deal with in formal models, you use learning models and agent-based models. And the complexity is for agent-based models technically open-end, although, and this discussion was also yesterday in Luke Steele's workshop, what you want to have is, according to Occam's razor, most simple model as possible to explain what should come out of the model. Okay. Now, I want to show you some application what you can do with this, because this was just a dummy thing, but even this dummy game was studied a lot. With different tools. I jump a little bit faster over it. If you're interested in literature, you can contact me. I just want to give you an overview what was done with this. So studying signaling systems. For two games, under learning dynamics, I showed you always this kind of signaling systems emerge, but it can also be shown if you have more complex kind of games, you get also this kind of structures, with kind of ambiguity, you could call it, or whatever, which are not evolutionary stable, but they have a reasonable Bayesian of attraction under evolutionary dynamics. You can study a phenomenon like division of pragmatic labor. What if we just look at this kind of game here? What would be fulfilled if wolf is much more frequent than cow? I think it's prior probability. Let's say wolf has 80% prior probability, and you use a shorter message for a more frequent state, you got this division of pragmatic labor. And if you have more states and more messages, you go in the direction of Zipf's law, what we will, in the next talk, also see something about this, Zipf's law of abbreviation. Okay, so here's some more. Let me just jump over it. Compositionality was so there's a model by Michael Franke about that agents can learn compositional structures without implementing it into the model, and this is always important. You want to have this kind of features as a side effect of, don't want to implement it in it. So you have very simple kind of assumptions, and you got more complex structure out of it. Vagueness was studied, a paper that you wrote with Michael. There's an ambiguity, or papers about ambiguity, and I maybe will talk a little bit about it in my case study if I have time. And then there are more specific linguistic features that were also studied with this kind of games. There's a study about the different vowel systems. And there, what is nice about this is you what kind of strategies are evolutionarily stable and compare it to maybe typological data. And there are a number of studies, especially Gerhard Jäger did a lot in this kind of area, shows that what he finds in the simple models, what's evolutionarily stable, matches very good to the systems you find most often. What this means is that evolutionary stability, so strategies or linguistic systems that are evolutionarily stable are expected to find much more often in languages of the world than non-evolutionary stable ones. Because the stability also means that they probably are more persistent over time. And then, of course, found more often in a specific point in time. There's something to basic color terms. There was also a talk by Tao Gong yesterday, and there are also people who use this kind of games to analyze the basic color terms lexicon. There's a study of case marking systems of semantic core roles, about the progressive aspect. So here in the direction of there are phenomena in grammaticalization who are very, very frequently found in the language of the world. So almost unidirectional, not completely, but specific tendencies, and you want to find out how this happens. And you can also use this kind of signaling game to analyze this. There's a progressive aspect study, and there's a study about negation, for example. I just showed you a subset about studies that are interesting for language evolution research, but these kind of models were also used, for example, in economics for job market signaling, and then also in animal communication, to study animal communication systems. Peacock principle, for example. Okay. There are also experimental approaches recently evolved, especially in University of Irvine, California, where they have a philosophy of science department, which is working extensively with this kind of models. And what they do is they just look how they use tools for experimental economics. We'll see later talk. It's also using this kind of approach. Use this to see what kind of signaling systems or what kind of communication systems emerge under different kind of conditions. Also one study where the interests are not completely aligned. And so as you can see, this approach combines a lot of different disciplines. So this is about economics here, and there are a lot of intersections of this research with economics. First of all, we talk about rational behavior of agents, but then also we abstract from this, and then we go a little bit to about philosophy and theoretical biology. But then again, we can focus on this again, right? If we have checked the model maybe theoretically, and then we go in the direction of linguistics and cognitive science, where we then model multi-agent models and artificial intelligence. So again, when we use theoretical biology, when we use evolutionary game theory, we completely abstract from this cognitive apparatus, how to model it, to see only what kind of dynamics, population dynamics would produce specific kind of features or make specific kind of strategy stable. And then on the other hand, if you're interested in have more realistic kind of cognitive abilities of agents, you have to go in this kind of direction, because again, it's hard to study this mathematically if it gets so complex. Okay. Okay, let me see. I probably have, a very short time. Let me just jump over this. So this is a case study about ambiguity. The basic idea is that we have a signaling game for states, and we have a context space. So receivers can get access to cues. So they can get external information not given by the sender about what could be the state. So this is how a strategy of this model would look like. We have four different kind of information states, and then the context are capital A or capital B, and this information is also given to the receiver. And this would how a signaling strategy in this system would look like. But you could also have a complete ambiguous system here, in the sense that A and B are used for two different kind of information states. But because you have this context information, you can come up with a strategy where communication is also super successful, 100% successful. So you have two strategies which work all the time. And what you also have is you have sender and receiver cost. So this strategy is more costly for a sender, because he has to use more messages. So this is how it's defined here. And this strategy would be more costly for the receiver because he has to access more contextual cues. And okay, let me jump over this. What you can show is if you only compare this kind of two strategies, you find that both are evolutionary stable. So we have here this one strategy pair is down here, all arrows go to this, the other one is up there. So of course, these are only two strategies of the whole game space. The size of the whole game space looks like this. It's a horrible big number, and you don't want to make a mathematical analysis with this kind of model, probably. So what you can do is, what I did is I used to use agent-based model. So I show you now how the combination of this kind of both tools are very efficient. And just gave this, like 300 agents, give them initially randomly assigned sender and receiver strategies. And use imitation dynamics that is produces very similar dynamics like replicator dynamics, and then I looked what kind of strategy types kind of evolve, and I found out that signaling systems and ambiguous systems evolve frequently, like I showed you at the beginning, but also what I call hybrid system also evolve. Hybrid system is a system that uses one message ambiguously and two messages in a signaling form, so it uses both together. And if you look what kind of strategies evolve, you find this evolves most of the time. So this is how often of all simulation runs these systems evolve. Sometimes non-optimal systems evolve. They are stuck in it, and since there is not enough noise, they cannot go away from it. But most of the time we found this perfectly working systems that use more or less degree of ambiguity and context success. And this is, if you compare these three strategies again in this kind of simplex, you find that this hybrid system top there has the biggest Bayesian of attraction with those roughly here, and these strategies have only this corners here. So, but the reason for this is because the sender and the receiver costs are very similar, and if you play around with both kind of costs, you see only when these costs are very similar, you find that this strategy, this hybrid strategy, is very successful. If you change this relationship to one or the other direction, you got one or the other strategy having a bigger Bayesian of attraction. This is the Bayesian of attraction I computed for different combinations. Okay, let me come to the conclusion. This model showed that if you have a signaling game with a context where contextual cues are given to the receiver, you can see the emergence and evolutionary stability of ambiguous systems. The costs help to make both evolutionary stable. You need both costs, sender and receiver costs. If you don't have costs, both are not evolutionary stable, and they can drift from one to the other system. And the relation of the cost is important. Which kind of these three strategies that I filtered out here are mostly successful? And so you can say that this cost represents speaker and hero economy. So when specific costs are high, the speaker economy is more or less important. And this speaker and hero economy kind of impacts the ambiguity level of the system. Thank you.